raise your hand or something in chat, whichever way. Are you able to hear me clearly? Okay, cool. All right, so obviously going to continue from where we left off yesterday. I did upload the actual recording on the YouTube channel, and you obviously have access to the same recording within the Teams environment. So whichever platform that you want to use in that regard, that's still fine. And like I did mention yesterday, and in that recording as well, that if you look at the network architecture playlist, you should obviously be able to find the definitive content that is relevant in that regard. So specifically the OSI model, access methods, conducted media, and then obviously network services and the IPv6 setup in that regard. So today, like I said before, we obviously want to continue from where we left off yesterday. Specifically, we looked at learning unit number 1, theme 1. So in today's session, obviously time permitting, we want to then conclude learning unit number 1, specifically looking at theme 2, and then jump into learning unit number 2, theme 1 and 2 in that regard, and then obviously learning unit number 3. So just to possibly look at just a basic recap. So I think yesterday we were just looking at the whole concept of signal propagation, and obviously mentioning the whole concept of what's happening with your routing mechanisms. So specifically packet versus your circuit switch, and then obviously working with the whole concept of frequency division versus time division multiplexing in that regard there. So I think what I'll do before we jump into the actual questions or definitive format of, I'm just going to share my screen in terms of my command line set up here so that you can look at what we were talking about in terms of the routing tables yesterday, something that you might have already covered in session as well. But just to make sure that you're all on the same page in terms of understanding what's happening with the hops, the routers, and obviously the definitive parts that packets take from source to destination and vice versa in that regard. So let me see if I can quickly just share my screen here. So specifically want to look at the command line setup in that regard. So hopefully that is visible on your screens as well. So what you normally want to work with here, like I said before, this is possibly content that you've already looked at prior. But if you're looking at the routing tables or the definitive routing mechanisms that we were mentioning yesterday as well, what you might want to then just type out here is root. So I think I'll use my lowercase mechanisms here. Doesn't really change much. So root, and then obviously the question mark for your help, so that it shows you the different aspects of that particular command, and obviously which switches to use in that regard. So once you type out root with your / and the question mark and hit enter, it should then display definitively what is happening with that command at large. So you'll normally have just a basic explanation of, so in this particular example, manipulates network routing tables, and then it shows you the different switches that you can obviously use with that definitive command for you to display something within your environment. So just for illustration purposes, what I want to then actually look at is the root print, which then enables you to look at your routing table in terms of your particular configuration. I'm just going to type out root print here. Right, and then if I hit enter, it will then show you the definitive configuration there within the IP version 6 and IP version 4 environment. So like I was just mentioning earlier on, if you look at what you got currently displayed there, your IPv4 routing table, it shows you active routes in terms of my current connection. And then obviously network destination, the network mask, which is also known as your subnet mask there. Your gateway, normally that's obviously the actual router that you're using to connect to obviously external network configurations there, the interface, and then obviously the metric in terms of measurement units in that regard. So that's a typical example of how you can then find or look at or literally just examine routing tables in terms of your current network connection in that regard. And then what you can also see there is IPv6. So remember, with the actual internet protocol versions, Definitively, 4 is default go-to when it comes to basic network connectivity. But obviously, because of some of the limitations in terms of quantities of IP addresses that are applicable, and some can argue when you're looking at it from a security mechanism as well, IP version 6 was then obviously designed to try and accommodate for those definitive shortcomings. So remember, IPv4 is a 32-bit address, and then IPv6 is a 128-bit address. So you've got a much larger addressing pool in that regard, and you're now using hexadecimal assignments as opposed to decimal for the actual numbering system in that regard. So you've got an IPv6 routing table, and you also have an IPv4 routing table in that regard there. And then one of the other commands that I also wanted to quickly look at that just solidifies some of the content that we discussed yesterday is the traceroute command. So this then looks at the hops. So remember, when you talk about a hop, it's obviously the movement of a packet from one particular router to the other, obviously until it gets to its definitive destination in that regard. So along any particular path, whether you're using circuit switch configurations or packet switch configurations, you obviously have routing mechanisms that are configured along that definitive path. And then the movement from one particular router to the other, from source to destination, is that the hop that I was just talking about just a couple of seconds back. So you normally have a maximum of about 30 hops configured within definitive network configurations. Anytime that you find that your packet doesn't reach its destination using those 30 hops as a maximum, then it obviously defines that there's a definitive issue associated with that particular link. Something might need to be done in terms of checking that link, checking the routers, checking the actual configuration in that regard, whether it's a security breach or an actual break in the link or an actual malfunction of some of the definitive devices that are plugged in along that route. So I'm just going to type out traceroute again here. So remember that the commands will be slightly different when you're working with, for instance, Linux or even Mac-based environments in that regard. So in some instances, you might actually need to type out the actual words in full there. So traceroute as an actual command when you're using different systems there. But with the Windows-based system, it's traceRT, which is short for traceroute. And then, like I said before, you can use your switch there with a question mark, which is the same thing as help for that definitive command that then shows you some of the options that you can use with that command. So you can check maximum hops, you can look at the host list, you can look at definitive target name, and you actually look at the options in terms of the switches that I was talking about just a couple of seconds ago as well. /D there does not resolve addresses to host names, maximum hops for H. Then you've got the timeout if you're looking at W in that regard there. So for argument's sake, if you want to look at how many hops it takes maybe to reach a definitive site. So remember, when you actually access a website, you're actually accessing a computer system, or you're actually accessing something that's hosted on a definitive machine or server in that regard. Those particular fully qualified domain names or website addresses can obviously be translated to IPs and vice versa. So in certain instances, you can use that to then check for connectivity along definitive routes in that regard. So if I was going to go and type out traceRT and then possibly /D there, and then put in www.google.co.za, obviously you'll find that there's a translation to that within the IP version 4 and IP version 6 environment. So if I was to then hit enter here, it should then trace the route from my current machine and my current network to this definitive site in that regard. So like I was saying earlier on, obviously translates it here to an IPv6 address, and then it shows you that it's trying to look at what actual path this takes over a maximum of the 30 hops that I was talking about just a couple of seconds ago. So I've got 11 of them. And then it obviously gives you the time frame. Obviously, dependent on how quick your network connection is. Obviously, you normally don't go beyond 5, really, in certain instances, dependent on configurations. But in all honesty, anything within that maximum is still applicable in terms of configurations. And obviously, in some instances, dependent on where you are, dependent on obviously the provider that you're using, and obviously dependent on actual network configuration that you've got, you might find that it takes slightly longer, but never above the 30 hops if there's a definitive connection that is configured appropriately in that regard then. Okay, cool. So I think that just speaks to what I was just talking about just a couple of seconds back in terms of again, maybe reiterating rather what we talked about yesterday and looking at what's happening with the hops, what's happening with the actual commands that you can actually use in a live environment to test that setup there. All right. So let's see what we can then do now in terms of the actual questions here. So let me see if I can go back to our presentation. And then what we actually want to look at is, see, that there. Okay, cool. So let me see if I can run an actual show on this. So there we go. So I want to look at theme number 2 within the Learning Unit number 1 environment. And again, still sticking within the confines of signal propagation, understanding exactly what's happening with links within your environments. Obviously, the focus as well in terms of actual content of the module at large is looking at OSI and TCP models, understanding exactly what's happening with your protocols, looking at security, and then also looking at your routing mechanisms in that regard. So here's a typical example of what I was talking about yesterday when I mentioned the fact that when you obviously have mark allocations associated with specific questions, there's content that you're supposed to be looking at that speaks to answering that particular question or those set of questions holistically. So in this particular example, we've got a 6-mark allocation for the first question. But if you check correctly there, you'll find that they're asking you to differentiate, right, between the two. So obviously a basic description or explanation of what path loss and multipath propagation is. But at the same time, they've asked you to use examples as part and parcel of our differentiation process in that regard. So this is where the marks obviously then come in. Normally you find certain scenarios where it's 2 marks for the explanation and then 1 mark for the example. Or in some instances, you might find 2 marks for the example, 1 mark for the actual explanation, but it's normally vice versa in that regard. And then again, like I was saying yesterday, you might find that the same question can come in with possibly a 4-mark allocation or possibly a 12-mark allocation. It all depends in terms of configuration. The more marks that are allocated to a specific question, obviously, the more content that you need to plug in that regard. But again, just make sure that you try and avoid getting bogged down on actual mark allocation when you're answering these questions, and just plug in as much content as necessary and relevant for what has been asked of, like we mentioned yesterday. And then obviously the second question is going back to what we were discussing in terms of wireless configurations, specifically here with your 4th and 5th generation network configurations. What they're asking of is when a specific device has been handed over from one particular base station to the other, they're then asking you to give the name of the network element that decides to initiate that particular handover in that wireless connection, and then state which particular network elements choose the actual target station in that regard. So what you now need to understand is when you're dealing with paths or multipath propagation, you'll understand that both of these are literally 2 essential channel impairments that can obviously degrade signal quality in that regard. When you're looking at path loss, what's actually happening within that environment is that degradation of a natural signal over a definitive distance, or a natural weakening of that signal over a distance. And then when you deal with multipath propagation, what you're actually discussing there is it describes a signal arriving at a definitive receiver via multiple different parts. What does that then do for us? It causes interference. So it's important to understand what these specific key wireless channel impairments do for us when it comes to network configurations, and obviously what mechanisms can be put in place to try and circumvent those issues there. So if you look at what I was just talking about just a couple of seconds ago, it's just looking at impairments that degrade an actual signal quality. Obviously, the longer the distance, the more degraded the signal becomes. You might now need to make sure that you plug in the appropriate mechanisms in place to ensure that signal quality is not jeopardized from source to destination when it comes to your network configuration in that regard. So just like I was saying a couple of seconds ago, when you're dealing with path loss, it literally refers to the natural weakening of a signal over a definitive distance. And then with propagation, that signal arriving at the destination via multiple paths, obviously, because of that multiple path setup, there's a lot of interference. Interference obviously then affects the actual quality of communication at large in that regard. But now, when you're looking at the actual differences with definitive examples, this is what you can then put across what you currently have on screen. So we just already defined the fact that you're looking at some semblance of degradation there in terms of the way in which a signal is passed from source to destination, and a definitive example that you can find in this regard is the obstacles that might be present within specific environments. So things like walls, furniture, and in some instances, even people can contribute to actual path loss by definitively absorbing or reflecting that particular signal's energy, and obviously reducing the strength across the board in that particular setup there. So you're now looking at it from the power of that particular radio signal diminishing over a specific distance. And a classic example, like I was saying earlier on, is an actual Wi-Fi router signal within a specific setup in that regard. So the closer you are to that particular router, obviously the stronger your particular signal is, and the better the quality in terms of communication or connectivity. But the further away you go from that particular access point or definitive router per se, obviously the quality of the signal becomes a lot less in that regard. And then you obviously have a less strong connection in that setup there. So that's what you can then put across in terms of the actual question at large there. So again, the definition, and then given a definitive example of what you've got on screen is just one typical example, but you can obviously look at it from a multi example point of view. And then when you're looking at multipath propagation now, so a classic example of this would be now if you're looking at an actual signal that's reflecting off objects, right? So these objects, again, can include the walls, the ceilings, buildings, and in some instances, even the ground as well, right? So anything that can literally be reflective when it comes to the actual signal at large can cause issues in that particular setup. And then I think what you'll discover in terms of a classic example of something along these lines is if you look at what we've got on screen, so that's the generic in terms of actual answer of. But the example that I was talking about, if you look at a classic example, is when you obviously have a Bluetooth speaker that's obviously connected to your phone. If you walk around a room, right, the actual audio might momentarily drop, right, or the sound becomes garbled, right, when you are in certain spots because you're not close to the actual source in that regard. And then obviously, this is often because the actual direct signal from your phone to the speaker is interfering with a reflected signal. So this is something that is important to remember when it comes to situations like that, when there's an actual drop in connection, or there's a drop in the quality of sound that is obviously coming from this particular speaker, as an example. So a typical example of that is one that bounced off an actual wall, right? So obviously causing two signals that end up canceling each other, right? And then in that particular setup, it's obviously within a specific location. So that causes a lot of issues when it comes to quality of your particular network connection. And again, it speaks to the wireless configurations that we've mentioned before. So this particular destructive interference where signals with opposite phases meet and definitively cancel is obviously quite common when you talk about multipath propagation. And obviously, what you can also argue is that it leads to a phenomena that's called fading. So that's something that you can also take into consideration there when you're looking at a definitive example that you can use when you want to discuss multipath propagation in that regard. Okay, so I think that then concludes LU1 in terms of the type of questions that come in. Remember, these are just definitive examples, like I said yesterday as well. Doesn't necessarily mean that this is the actual question that comes in, but it gives you a bit of an overview in terms of what type of questions are coming in terms of format, and also looks at what is happening in terms of the actual content of. So this helps in terms of focus of the actual module content in that regard when it comes to preparation for the assessment, specifically the test and the exam. I think with the assignment, it's slightly better to a certain extent because you obviously have the definitive resources, but when it comes to your test and exam, remember it's a closed book assessment. So the focus becomes a bit different in that particular setup there. So let's see if we can then dive into LU2 now, learning unit number 2. And this now looks at the OSI model, specifically looking at definitive protocols, working with the internet or TCP/IP model in that regard, understanding exactly what's happening with the transmission control protocol, what's happening with the user datagram protocol, what you can actually say between the two in terms of one being a guaranteed delivery platform as opposed to something that's effortless. Why? Because there's no acknowledgement that is obviously expected from the receiver in certain instances. So now it's important to identify now in which environments these are used, and ultimately, what can you also mention from a server-side configuration in that regard? So if you look at what we currently have on screen, again, two questions that speak to content within that protocol environment or service configuration as well. And with the first one, you want an 8-mark contribution. And specifically what you're discussing here is the 4 broad classes of services that a transport protocol can provide. And it then mentions that for each of these particular services, indicate whether you're looking at UDP or TCP. So remember, UDP, like I was just mentioning a couple of seconds ago, is your user datagram protocol. It works on the transport layer of your OSI model and within your internet and TCP/IP configurations. And what normally takes place with this type of protocol or this type of service or procedure is that when you're looking at two particular entities, right, so source and destination, it doesn't literally wait for an acknowledgement to confirm that a message has been received, right? So it's also known as effortless in that regard. So a lot faster because there's no need for acknowledgements that are being sent. But again, it's not as definitively reliable because you could be sending messages that are not being received, messages that obviously are either also received in a diluted fashion, right? So you want to avoid certain scenarios in that particular setup, but there's an argument that dependent on the actual configuration that you've got set up, there are certain instances where that effortless delivery is particularly applicable. And then obviously when you discuss TCP, transmission control protocol, on the other hand, slightly slower, but it's guaranteed because we need to be getting some kind of acknowledgement from the receiver that a message has been received and has been received in the right format, has been received without any particular issues when it comes to quality and when it comes to security in that regard as well. So because of that, it becomes slightly slower because we have to actually wait for an acknowledgement before we start sending possibly another message or another part of the message. But again, like I was saying a couple of seconds ago, it then becomes a bit more solid in that regard. Why? Because at least we know for a fact that whatever we sent has been received. And if it hasn't been received, we get an indication of, and at the same time, if it has been received and it's not in the correct format or it's been particularly jeopardized, we also get that confirmation in that regard. So that's the definitive differences between the two. So if you're looking at it holistically, one is guaranteed, one is effortless. The other one is looking at it from a definitive point of view, slightly slower, but obviously you get guarantee in terms of communication. The other one a lot faster, but obviously not reliable. So we're looking at four different definitive classes there. And then the second one, you're looking at uh, working with a web server configurations here. So consider an HTTP client that wants to receive a document given a definitive URL. The IP address of the actual hypertext transfer or transmission protocol server is initially unknown. What transport and application layer protocols now, besides obviously HTTP, are needed in this definitive scenario? So you might also be given snippets in terms of what is been received from the actual server, and then be asked to literally decipher that particular snippet of a message that comes from the server in that regard as well. So let's see what we can do in terms of answering these particular questions. I think if you look at question number 2 there, in terms of what you currently got on screen, it also goes to this particular snippet that I was talking about earlier on, where you now have a snippet that you're given, and then you're asked to deduce what type of information can you actually make sense of from that particular snippet that has been incorporated there. So the current text that you find on screen is showing a reply that is sent from the server in response to an HTTP GET message in that regard. So the type of question that you can find for this specific type of snippet is, was the server able to successfully find the document? And then obviously then mentions something like what type of, or what definitive time was this particular reply provided? So these are some of the questions that you can get. Another type of question that you can get regarding this particular snippet is when was the document last modified? So what can you actually see within the actual snippet that gives you an inclination of that particular question there? Another one that you can also get is how many bytes are there in the actual document that has been returned? And then lastly, you can also even get questions that will ask you what are the actual the first bytes of the definitive document there. All that information can be deduced from what you find on screen, but we'll look at that in a moment in terms of how you can then make sense of this particular snippet and obviously the questions that you've been asked. So I want to obviously go back to the first question here, looking at the actual 4 broad classes. So it's an 8-mark question. The argument is obviously 2 marks a piece in that regard. But again, like I've said before, as much content that can be plugged in that is relevant, what has been asked is obviously appropriate in that regard. So the first thing that you want to discuss here would obviously be reliable data transfer, like I was talking about earlier on, right? Which literally ensures that we get some kind of acknowledgement from the receiver to say transmission has been taken place. I've received that particular message or packet, whichever way, within a definitive time frame, by the way, because remember that also enables you to create a baseline where you can check for quality of network connectivity, or you can also even check for security breaches, like we were mentioning yesterday as well, to say if it's supposed to take a specific time that has been already recorded and monitored over a course of transactions or course of transmissions, anything that is outside the confines of that predefined baseline can be an indication that there's a problem with the actual link. That problem can indicate the actual link itself, physical or otherwise, can actually indicate the gadgets that are used or devices that are used along that particular path. So the routers or the computer systems, whichever way. And it can also even identify if there's been a security breach during transmission in that particular setup. So the first thing that you want to discuss here, as you'd see on screen, as part and parcel of answering that question, is the reliability of the data transfer that I was talking about just a couple of seconds ago. And it also speaks to the acknowledgements I was mentioning. So normally you'll find that those acknowledgements are shortened to a capital letter ACK as a definitive acronym for that acknowledgement or representation of what acknowledgement is about within that communication space in that setup. So if you look at our third sentence there, if the sender does not receive an actual acknowledgement for a packet that has been sent within a definitive time frame, there's an assumption that the particular packet has been lost during transmission. So obviously that you can also even assume that the quality of that particular packet has also been jeopardized. So it resends until you get an acknowledgement. So that's where the guarantee comes in that unless we get an acknowledgement from the receiver, we continue to send that particular type of packet or message in that regard. So that again ensures that all particular data is received. And like I was mentioning earlier on, TCP is part and parcel of this, right? So it provides this particular service. Obviously, UDP does not, because remember, UDP is effortless. It's a lot faster. It doesn't wait for any acknowledgement. It just sends and assumes that whatever has been sent has been definitively received. So this is something that you also need to take cognizance of when you're then answering this particular type of question in that regard. So reliable data transfer, we're looking at acknowledgements, and then at the same time, if you're looking at it holistically, the TCP obviously provides for this, but your UDP does not in that regard. The second one that you want to also deal with here would be reliable data transfer. Not reliable data transfer, sorry, that's the actual first one. We're looking at the second one being congestion control, right? So obviously within any particular network environment, every time that you look at connectivity, there could be a scenario where a particular path or connection gets overloaded. That causes congestion. That means that there's a bottleneck in terms of that particular connection. Becomes a lot slower, and there's obviously a inclination there that the quality of whatever has been sent and ultimately received is jeopardized as well in that regard. So there has to be something that identifies that there's congestion that has been taking place, find possibly alternative routes, or definitively try and slow down traffic along that specific route there to avoid any discrepancies there. So again, if you look on screen, that's the congestion control I was mentioning just a couple of seconds ago. So in instances where you find that your sender is sending messages or data a little bit too quickly, you can then slow down at that particular connection just to avoid the particular network being overloaded. So normally you might find that certain terms like throttling is associated with a network configuration or network connection, which is just the slowing down of a particular network dependent on the amount of data that is being sent along that definitive path. So particular algorithms obviously will then be able to identify that there is some kind of congestion here, or data is being sent a bit too fast in accordance to what is currently being set up, and then slow down that traffic or throttle that traffic to ensure that we avoid issues in that particular setup. So once again, with this particular type of service, TCP does provide for it, right? It's part and parcel of its definitive mechanism. But remember, again, because of the effortless nature of UDP, it doesn't provide for this particular congestion control because, again, it just sends with a generic assumption that whatever has been sent has been definitively received in that particular setup. So there's no change literally in the actual speed of transmission. Neither is there a particular change in the actual configuration of the link that is there within that environment there. So that's the second one. The third one that you also might want to discuss here now is literally the definition of what TCP would be, which is the connection-oriented service, ensuring that there's a logical connection that is created first. Once that particular logical connection is confirmed, then utilization of the physical connection there, whether wireless or bounded, is then configured and obviously utilized in that regard. So there's that logical connection. Think of it as a testing mechanism to see if there's an actual link between sender and receiver, right? Once that has been confirmed, then the actual transmission takes place. So to avoid a situation where packets then ultimately get lost along transmission, there's a testing mechanism that is there within TCP to say, do we actually have a link between these two entities? If there is a link, then we can now utilize that definitive link to actually send. So the third one there, the penultimate one, in terms of this particular question, again, like you see on screen, is a connection-oriented service I was mentioning earlier on. So this then, like I was talking about, there's supposed to be a logical connection that is definitively established first before any particular physical data can then be sent there, right? So this guarantees that at least there's quality in terms of transmission, and at the same time, what it also speaks to is that it avoids any particular discrepancies from a connection point of view in that regard. So if you look at it holistically, after the actual data has been data transfer has completed, then obviously there's no need for the connection. So this also looks at efficiency as well, to say there's no need to keep a connection live if we're not going to be sending any particular data across that definitive channel. So that is to a certain extent the brilliance of TCP, although there's an argument, like I was saying at the beginning, that slightly slower when you're looking at specific mechanisms in that regard. So that handshake, obviously, the two-way system that obviously enables and manages the flow of data. Once again, TCP provides for this because that's literally part and parcel of connection-oriented services. But obviously, once again, UDP does not provide for this. So it's connectionless, right? So this doesn't naturally mean that we don't have a link between the two entities, but there's no need for a logical connection before we look at actual sending in that particular setup. So that last sentence that you find on screen just reiterates what I was just mentioning over the past minutes or so, to say it simply just sends packets without prior setup. So that's our penultimate one. And then the last one, obviously, that then concludes that first question would be that multiplexing and demultiplexing. So remember, with multiplexing, like we said yesterday, normally a combination of multiple slow speed channels into one definitive high speed channel for management of infrastructure and obviously security mechanisms in that regard, so that there's no waste of utilities with dedicated channels that are not always used. And at the same time, it provides for security mechanisms because bits and pieces of data are sent are collected from multiple systems and sent as one definitive packet across that link, and then obviously demultiplexed at the receiving end in that regard. So obviously, what you then need to take into consideration here are the abstract port numbers that are relevant within your network configurations. So when you look at a physical connection, you actually plug in, for instance, a cable into a definitive port. But then when you look at it from an abstract point of view, these particular protocols and services will have predefined ports that speak to what type of protocol or what type of service that is being used at that particular point in time. So for argument's sake, when you look at HTTP, your hypertext transfer protocol, normally that's associated with port 80, right? And then when you look at the secure version of, over the secure sockets layer, you also have a different port in that regard that accommodates for that particular mechanism there. Same difference for FTP versus SFTP and so on in terms of connectivity. Normally, you find you've got about 65,586 ports, if my mathematics serves me right, that you can use within these particular protocol configurations. obviously it's all dependent on the environment that you're in that particular setup. So like I was just mentioning earlier on, when you look at it from a web browser point of view, obviously HTTP is the default go-to, so that's port 80. And then obviously when you're looking at maybe sending mail, so when you deal with your simple mail transfer protocols, when you deal with post office protocols as definitive configurations, you also have dedicated ports. So while an email client a port there would be 25 in this example. So the interesting thing about this multiplexing and demultiplexing now is that both TCP and UDP then obviously provide for this service. Why? Because both of these particular platforms use port numbers or use ports, right? So remember, the actual difference is in the way in which you are sending and receiving data, right? That logical connection, the guaranteed delivery, the acknowledgements we're talking about, connectionless configurations. But when you look at it from what actual mechanisms you're using, both of these protocol standards use definitive ports there. So of the actual four, three of them are dedicated to your TCP specifically. And what are these three? Reliable data transfer. That's the first one. Congestion control is the second one. And then obviously the third one is connection-oriented service. And then what both of them then definitively utilize would then be your application multiplexing and demultiplexing in that regard there. All right, so I think that speaks to that definitive setup in that regard. What you want to now look at is understanding that snippet we were talking about earlier on, and then obviously looking at what information you can deduce from that snippet when it comes to your configurations holistically there. So if you look at what we were talking about just a couple of moments back, normally you're looking at understanding what's happening with the server. Was it successful, or was it successful in terms of finding the actual document? What's happening with timestamps? What's actually going on with the actual modification? And the other thing that you also might want to talk about is understanding what's happening with the whole concept of setups in that regard. So I think the if you're now looking at it holistically, let me see if I can go back to that snippet so that you can see specifically what we're talking about in this regard. So if we go back, there we go. So like I was saying earlier on, you're looking at, like I was saying just a couple of seconds back, that this current text that you find on screen literally shows the reply sent from the server in response to an HTTP GET message. So remember, normally when you're looking at connections, you got GET and POST messages or configurations that can be used in that regard. So here we're looking at a GET message. And in essence, what we're looking at, obviously, we're considering a situation where a client wants to retrieve an actual web document, right, at any particular or at a specific URL, right? And obviously, the IP address of the HTTP server is initially unknown in this particular example that we've got. So once again, we're considering a situation where a client wants to retrieve a web document, right, at a given URL, but obviously the IP address of the definitive server here is initially unknown. So first of all, we're looking at a situation where was the server able to successfully find the document, and then what time was the document reply provided? So if you look at this particular snippet carefully, so let me see if I can actually maybe activate my pen here. Right, so if you look at it carefully, right, we can definitively confirm that the server successfully found the document. Why? Because we've got a status here. If you look at this carefully, we've got a status of a 200 OK, right? So that literally indicates a successful request, right? And then the actual document reply was provided on Tuesday, the 7th of March, 2008, and specifically at 12:39 and 45 seconds at GMT time. So that's the information that you can deduce from such a question, right? So once again, what was the question? Was the actual server able to find that particular document successfully? And then what time was that particular document found? If the answer would be yes in that regard. So first of all, first part of that question, yes, with the 200 OK message that we find here. And then again, in terms of actual reply that was provided, that is the actual date that you find that is currently highlighted there or underlined in red in that regard there. And then secondly, now, another question that you can look at or information that you can deduce from this particular snippet, when was the document last modified, right? So again, you have this particular part here, last modified, as you can see currently underlined. It mentioned that it was last modified on Saturday, the 10th of December 2005, and then it actually has a specific timestamp in that regard of 27 minutes past 6 with 46 seconds GMT time in that regard. So that's information that you can also deduce from that definitive snippet. And then with another question there that you can also look at, how many bytes are there in the document being returned? How many bytes are there in the document being returned? Again, do you see where it says here content length, right? That then specifies this particular path here. So that content length would then be obviously 3,874 bytes, right? So that's also content that can be directly plugged off this specific or something that you can plug out when it comes to this specific snippet. And then what are the first 5 bytes of the definitive document in that regard? So if you look carefully as well, it's an HTML document naturally that you're looking at. The first 5 bytes of the document are obviously going to be this particular part here, right? So you've got your doc type set up in that regard. That's something that you can then also plug out in terms of the actual document itself. So it will have so these are the first 5 bytes that we're talking about specifically, right? Because your document would start there with document type HTML. So that's something that you can then also take into consideration there. So that's how you can then possibly read content directly off definitive text reply that's obviously coming from a server, specifically using the HTTP GET message in that regard. So I think that covers us in terms of that particular part there. I think that also then definitively speaks to learning unit number 2 holistically. I think we've got about 12 odd minutes, 11 now. I think we can look at possibly the first 2 questions of learning unit number 3, theme number 1, and then we can, time permitting, possibly look at the third one. If not, then we can then always look at our session next week to cover that particular part. So what we want to look at would be these questions. Yeah. All right. So first of all, so that's learning unit number 3. Now looking at theme number 1, describe why an application developer might choose to run an application over UDP rather than TCP. Use appropriate examples to explain your answer. So this is what I was talking about now earlier on to say, while if you look at it on paper, obviously the argument would be possibly someone would be, okay, listen, I'll just literally just go TCP because it's guaranteed and so on. And get acknowledgements, it's reliable. But here we're getting a question which then says that one that is not reliable, that is connectionless, that is effortless, that is a lot faster, but with no guarantee. In which environments would an actual application developer choose that over something that is guaranteed, over something that is reliable? And then obviously we need to have specific examples of. And then the second question there is asking us, why is it that voice and video traffic is often rather sent over TCP rather than UDP when it comes to today's internet. So there's a 7-mark allocation for the first question, and obviously a 4-mark allocation for the second one. So if you look at what we have, right? What are we actually talking about in this particular setup? So when you look at application development, right? Normally what you're looking at is utilization of your application, obviously over the internet space. You're looking at speed and low latency, right? So in certain instances, you might want to argue that when it comes to a specific application, what you're prioritizing is actually speed and low latency over reliability. But then the biggest question still remains: in which environments would we actually sacrifice reliability of connectivity or reliability of configuration, prioritizing speed and low latency in that regard? Remember, like I mentioned before, UDP is literally a connectionless protocol that doesn't have any particular overhead, right? Why doesn't it have overhead? Because it doesn't wait for any particular acknowledgements from the receiver, right? When it comes to an actual connection. And then obviously, what you're looking at in that particular overhead, establishing the connection so it doesn't have to look at logical connectivity first. It doesn't have to manage acknowledgements, and at the same time, it doesn't have to implement congestion control. So if you go back to, let me just go back a couple of slides. What we're saying is TCP, I mean, UDP rather, does not have to worry about a reliable data transfer. Neither does it have to rely on congestion control. Neither does it have to look at some connection-oriented service. So that logical connection I was talking about, there's no need. Congestion control, no need. And obviously managing those acknowledgements, like we were mentioning earlier on, is something that UDP doesn't need, right? And what does this then do? It makes UDP a lot faster. And you can argue that it also makes it a little bit more efficient for specific applications or for specific types of applications. So this is the way the key issue is, that it's important for you to remember to mention that it's only for specific applications. So it's not faster and more efficient overall, but it's faster and more efficient specifically when it comes to different types of applications. So what are these applications? Let's have a quick look at what these would be. So, okay, so that's our second set of questions. This is what I was just mentioning, right? So if you look at on screen, low latency versus over reliability. And again, like I was saying earlier on, makes it faster and more efficient only for certain types of applications. So what would these then be, right? Which applications would not need to be bogged down with acknowledgements? Which applications would not need to be bogged down with congestion control? Which applications would not need to be bogged down with a logical connection first before actual configurations take place in that regard? So the first one that we can look at specifically, and then obviously specify the example of. So remember, we mentioned speed being more important than reliability. And then at the same time, you're looking at a scenario where your simplicity might be key here in terms of connectivity in that regard. So what you're actually looking at is specifically here, where you're looking at speed versus reliability. A classic example of this would be online gaming, right? Because when you're looking at, for instance, player movement within specific environments there, these actions are constantly being sent to a server, right? So if a single packet is obviously lost, so when it comes to things like player position and so on, it's not necessarily a big deal, right? Because obviously the next packet is literally sent within milliseconds, right? Which will obviously contain that particular updated position. So because of that, there's no need for us to then utilize TCP in this setup, because retransmission within the TCP environment, remember, TCP waits for an acknowledgement. If it doesn't get an acknowledgement, it continues to resend until that acknowledgement is received. But then in a situation where we're dealing with online gaming, that can produce latency that we're talking about earlier on, and that can produce a lag. And when you've got latency and we've got lags, when it's online, when it's an online game, then it's a massively poor user experience. So that's something that you want to avoid when you create something along the confines of what we were just discussing. So again, most common reason is to tolerate a small amount of data loss, right? A minimal amount of data loss. And obviously where real-time performance is key or is of the utmost importance in that particular setup. So remember, like I was saying, UDP wouldn't waste time in terms of checking whether a packet has actually been received because it doesn't get an acknowledgement, and there's no need for retransmitting anything in that particular setup. That's the reason why that UDP becomes a lot faster in that regard. So as your contribution in terms of answering this question, obviously we're looking at speed being a lot more important or prioritized over reliability. What are the examples that we're talking about in this particular setup, the online gaming configuration? And again, you can then mention that within that online game, a classic example is a player position, for argument's sake, because this changes like every particular millisecond, literally, as you're moving within definitive maps, for argument's sake, in that regard there. So retransmission would then cause a lag, and then that particular lag would then affect actual user experience. So that's the first one. And then when you look at the second one, and now, right, in terms of definitive examples of in this particular setup, one thing that you can then also mention is when you're dealing with streaming. Again, streaming is live, it's real time. So again, if you've got drop packets, you then find there could be a glitch in audio, there could be a glitch in the actual video or picture that is being presented on screen currently. But again, if we look at a scenario where we now need to resend that particular picture or resend that particular dropped audio and so on, it then affects the actual quality, and it literally becomes a bit disruptive in that regard. So again, if you're looking at a situation where conversations are obviously live, we're supposed to move forward. So whatever data is then retransmitted is no longer relevant at that particular point in time because that point has already passed. So if you can't then have a situation where you continuously repeat content, it doesn't provide for a smooth experience. So this is another example that you can then obviously use within that environment there to say, when you're looking at video or voice streaming, you want to ensure that there's a smooth way in which that is undertaken. And again, like I was saying earlier on, a drop packet is nothing to consider here because even when we lose connection, when you come back again, you're already at a different part of that conversation or a different part of the actual video itself. So this is also something that you can use to say when you're working with configurations, UDP becomes a default go-to here as opposed to TCP in that regard. Remember, like we were saying earlier, the TCP is guaranteed. So it's always going to be a lot slower. And in certain situations, like we're talking about the streaming and the online gaming, this becomes a cumbersome process in that regard. And then the other thing that you also might want to talk about now. So remember here, we were mentioning the fact that we're looking at speed being more important than reliability. And then in this particular instance, another thing that you can then also look at with that same question now is looking at understanding what is happening with simplicity being key, right? Why is it simple? It's connectionless. Obviously, there's a less lot code involved in terms of resource configurations as well in that regard. So a classic example from a networking point of view is DNS. So remember, DNS is short for domain name system. That's what is responsible for translating an actual IP address, be it IPv4 or IPv6, into a fully qualified domain name or an actual name that we're all familiar with in terms of a web address. So again, a classic example where this is relevant because obviously when you're looking at it from a definitive setup, you're looking at situations where your computer system sends a small single packet to query the actual DNS server. But here we are now looking at trying to update or get actual web addresses in that regard. So DNS would be a perfect example of why this UDP utilization would be relevant there. Because again, if you're going to be using TCP, again, it's a three-way handshake. So remember, you need to have the logical connection first, then have a response from that, send acknowledgement, get a response from that before you actually look at getting a definitive query resolved there when it comes to your DNS configurations. So it can cause a host of issues from a efficiency point of view because speed is obviously jeopardized there. So that's something that you can also consider in that regard. So I think that's unfortunately what we have time for in this particular session. What we will then look at possibly next week's one is discuss. So this was the other second part would have been, yeah, this one here, because this is what we just definitively discussed, right, in terms of configurations. I think specifically it was question number 1 there for the 7 marks. So we'll look at the second question, which is looking at why obviously voice and video traffic is sent over TCP. I think that we might have already answered that, possibly superficially so, though, in terms of working with question number 1, but we'll look at that again in a bit more detail in our next session. And I think the third question, which then concludes content in that regard for this test revision, will be the one that you find on screen. So we'll discuss that obviously next week as well, and then possibly just jump into a couple of assignment-based questions there before we start also looking at revision or content that is relevant for the upcoming exam. All right, so I think that sorts us out for today's session, right? Let me see if I can, right. Okay. All right, so that sorts us out in terms of this particular session. But before we call it a day there, do you have any questions, contributions, or any particular concerns? So that's fine. So, like I said before, I will upload this onto the YouTube channel as well, and then provide the link on Teams. And that same recording would also be available on Teams as well in that regard. All right, then. Thanks for attending. Enjoy the rest of your day. We'll then convene again in next week's sessions. Cheers.